Announcements as we get started. These are the announcements that everyone who walks in late wishes they were here for. First is that the homework is extended till Friday for everyone, which is good. I had a few requests for that, and also just given the difficulty of this assignment, the fact that a lot of people focused on the exam through Friday and then probably needed a little bit of recovery after that exam over the weekend. So I will be getting the next assignment to you probably tomorrow. I'm working on that with the TA right now. So homework due Friday. I still urge people to work on it over the next few days because it's kind of a beast. It isn't the most questions, but a lot of them are quite difficult, especially if you are learning the pumping lemma and still getting used to the pumping lemma, and a lot of those questions will take quite some time to understand. The second is that question 13 on this current homework is being turned into extra credit. And the reason for that is that the wording of the PDF is incorrect, but the Canvas rubric wording is correct. So if you're aiming to do that for extra credit, make sure you look at the Canvas rubric for question 13 before finalizing it, because the PDF document is incorrectly worded. Plan is still to, I hope to get exams back to you by Friday. I will have a little bit more news for that as I figure out the graders' productivity this week. You had quite the list of tasks to do, and they were not short, easy tasks. Questions on that or the class as a whole? I guess I should note that I would hope people are willing to attend office hours over the next couple of days. The way that I'm advertising it is that I'm throwing a party in my office. There will be no food, no alcohol, just stress and productivity. It's a great advertisement. I hope you all take me up on that.
Say you have food for thought.
Yes, I like it. It's down the out the hallway on the top floor. You know, take a left. That was a stretch, but I did what I could with 3 minutes of time to think about it, 3 seconds of time to think about it. All right. Last time we were talking about simple grammars. And so we just found that it was a fairly simple couple of rules to determine whether a grammar could be simple or not. And we'll come back to this concept of a simple grammar when it becomes relevant in our studies, but I thought I would, since it's a very small change from our context-free grammars that we're talking about now, this is a fine time to introduce it. But what we're going to dive into next is the concept of grammar ambiguity in more detail. We defined it last time and talked about how a grammar was ambiguous if there was a string in the language such that we could take 2 different paths through the productions of that grammar and generate that same string. Another way to think of it now that we've talked about parse trees is that we could construct 2 different parse trees that derive it. Let's give you another example of this, but now with parse trees. So here is a grammar that only has the non-terminal s, so I can go to A capital S B or capital S or lambda. We saw this before as what could create mathematical parentheses or nested control structures that allowed for sequential nested control structures. So let's take a look at how to construct AABB. In mathematical parentheses, this is open parentheses, close parentheses, close parentheses. In nested control structures, then this would be some kind of loop within a loop, or an if within a loop, or something where the control structure is directly nested. So go ahead and see if you can come up with a couple of parse trees from this that generate this same string. just came to me. BYOB, bring your own brain. For those who just came in, you missed an important announcement at the beginning of class. For those of you who are here on time, this is an excellent opportunity to extort them. What do we have for parse trees? A couple ways to do this. We could start with S. I like to kind of, you can either have them on the arrows themselves in the actual nodes, doesn't particularly matter. But if we're expanding this S in some capacity, we can either go to ASB and have this S go to ASB and then go to lambda. So adept for search AABB. We could also have this S go directly to SS, have each of these go to, I guess one of these needs to go to lambda. One of these needs to go to ASB, and one of these needs to go to ASB, and then this needs to go to lambda. So you could flip these and it would be exactly the same, doesn't matter. So many different parse trees that you could generate here. In fact, you could SS as many times as you wanted and just make sure that one of them has this substructure to it and the rest just go to lambda. You could do that an arbitrary number of times. So there are in fact an infinite number of parse trees that you could generate. Everyone in this class is too moral. I would have been all over trying to extort my fellow classmates for money. But since no one is trying to do it, I will say for everyone else that the homework is extended till Friday. And that question 13 on the homework is now extra credit. If you are doing this, then you should follow the rubric and not the PDF. The PDF had a typo. Thus the reason for it being extra credit. All right, so the ambiguity that we see in grammars like this, in English, somehow that's okay. I don't know, I personally hate ambiguity in spoken in natural language. When I say this to my English major mother, she says, that's the beauty of spoken language. It's the beauty of written language, is that you can tell a story in very different ways and you have options as you communicate. And as a logician, I say this is terrible. I want to know exactly what you mean with no ambiguity whatsoever. So I don't make any claim about spoken or written language. That's not my expertise. That's not something that I have any say over. But in computer science, it is terrible to have ambiguity. So what ends up being important with regards to our grammar is it will not be good enough to just write a grammar that represents the language, but we need to write a grammar such that there is no ambiguity in the parse trees. So we can very frequently rewrite grammars to remove the ambiguity that is inherently in them for many strings or many different paths through that grammar that can produce the same idea. So let's talk about what options we have to remove ambiguity in grammars. So one thing that I've been hinting at a little bit with regards to the language that we've been looking at, the grammar that we've been looking at, is that we can represent mathematical expressions with a grammar. Let's take a look at one potential grammar for mathematical expressions. Here we go. We have a non-terminal E, we have a non-terminal I. E can directly become I, E can become E plus E, E times E, or we can throw some parentheses around an E and then recurse in the middle. I now is going to be our legal variables, A, B, and C. And in this world of math, the only symbols are plus, times, and then we can throw parentheses around things as well. So questions I have for you about this. So restricting things to A, B, and C, but what is the order of operations for expressions in this grammar? Is it the same as the order of operations that we are used to in math? Or is there something about this grammar that changes that in some capacity?
Isn't it the same?
What do you mean by the same?
Like, I just don't understand. If we construct it, then wouldn't we just follow the order of operations?
Do we have to, though? If we construct an expression, E plus E, the first E becomes an I that becomes A. The second E becomes A times. Then we end up with and the times, because the first E of that becomes a B and the second becomes a C. Let me just draw that out of the parse tree. So we're going to start with an E, that is the base symbol. That E is going to go to E plus E. Then this E is going to go to I that goes to A. This E is going to go to E times E. And this is going to go to an I that goes to a B. This is going to go to an I that goes to a C. Does this say that we should do the plus or the times first?
Doesn't say.
It doesn't say anything. It's ambiguous. So if we allow for, this grammar allows us to represent any mathematical expression with pluses and times and parentheses. However, it allows us to create expressions that need to be further, there need to be rules that are further specified in order to know how to evaluate what is there. It's not in the grammar itself. It relies on outside rules. So you could write a compiler for which this is a perfectly reasonable grammar, but the compiler interprets this as the plus comes before the times. You could write another compiler where the times comes before the plus. It's not inherent in the grammar. The grammar doesn't force an order of operations. So is it possible to remove this ambiguity from this grammar and force an order of operations directly from the grammar? And the answer to that is yes. So we should see how that's done because it's really cool. But first, I want to give you some time to play around with that idea. I don't expect that people are going to get a solution, but take a few minutes and see if you can intuit how you might change up this grammar in order to prioritize multiplications before additions unless there are parentheses surrounding the addition. That when you have something like this, that it does force the order of operations. What tools inherent in grammar construction would you need in order to force that?
Parentheses.
What was that, sorry?
Parentheses.
Right, to be able to force doing multiplication before addition when there are no parentheses. The parentheses would still override that order of operations. But can we force the order in which they're evaluated in some capacity? I'll at least introduce the idea before we go back to it. So something like, yes, evaluate A plus B times C. Here's one parse tree, here's another parse tree. And if we're doing a depth first search to do this, which one gets prioritized if we're doing this particular parse tree? So depth first search says, we're going to look at this in depth first order, but note that this E is unknown at this point. We have to evaluate, we have to go through this entire depth first search before we can evaluate the E times E. That gives us this E, and then we can finally evaluate the E plus E. So this parse tree says times before plus. And this parse tree now has the information to do this addition before it goes back and does this multiplication. So here we have multiplication before addition. Here we have addition before multiplication. And it's ambiguous which parse tree we should construct to be able to evaluate them in an order. It's not inherent in the grammar. Any questions on that, or why these have different order of operations inherent to their parse trees? The grammar allows for both of them. That's a bad thing. We want to design grammars that adhere to the mathematical rules that we as a society abide by. Who knew that when memorizing orders of operations back in grade school, we'd have to later justify it. Really, it's a cultural thing that we have done to say that we're prioritizing this ahead of that, but it's because of ambiguity. We have stated that this is the rule that we are using to resolve that ambiguity. There's no other reason. We could have, as a society, decided the plus comes before times. So we build precedence rules in whenever we have ambiguity because we all want to interpret things the same way. Ambiguity is bad in logic. The rules for the order of operations exist outside of the scope of the grammar. So when we create the grammar, we have to abide by those outside standards. We can rewrite the grammar to encapsulate the precedence rules. What do we think? What changes could we make to that grammar to try to enforce precedence? Try to enforce a correct order of operations. This can be a very broad idea. What broad change could we make? What's missing from that grammar, or what changes do we need to make? Any just thoughts or guesses? Yeah.
I was thinking maybe having E, well, I thought about it, I think this is wrong, but having E go to E times E, and then having if you want to add E plus E, you must go to a different production, not E going back to itself, but E going to a different.
Very smart. Yes. So just like we saw with the parse tree on the last slide, when we do a depth first order, we need to force that order going through the correct order of operations so that we evaluate times before plus. So really all we need are more non-terminals and to create a loop of those non-terminals that go through the order of operations and force an order to the parse tree that does that. That's exactly what we need to do. So here's an example. E stands for expression, T stands for term, F stands for factor, and I forget what I stands for. Some terminal. We'll go with that. Take a second look at this. Spend some time trying to understand why does this force an order of operations? If you have a couple of ideas, talk about it with a neighbor or small group. This might help you. Here's that same A plus B times C, but now this is the only parse tree we can generate for it. Convince yourself why that is and how that forces that order of operations. Any thoughts on this? Anyone want to share their perspective or their analysis? I see it as like a stack. In order to evaluate an E, in order to evaluate an addition, we have to evaluate the E and the T. And we can at any point go all the way through the stack to create a variable. But if we're going to create a multiplication, then it has to come in the deeper down than that addition. Unless we cycle all the way through to parentheses that allow us to override that and create an E, but the E has to be surrounded by parentheses, which allows us to override the whole stack. But by forcing them in this particular order, it forces the multiplications down deeper into the parse tree. Again, unless we override with parentheses. So we can make an addition immediately, but if we skip the addition and go directly to a multiplication, then there's no way to put an addition deeper in this without an associated parentheses. Once we start something that is higher order, deeper down in the parse tree that will be evaluated before what is shallower in that parse tree, there's no way to create something of lower precedence down here, unless we override the order of operations. So that's very clever. This is not something that I would expect people to be able to do on, especially in an exam, or really even on a homework. There's too much interpretation here to generate something like this, but I think it allows us to appreciate the work that's been done to be able to create a grammar like this and force a particular order of operations. That's really cool. Looks like about 2 of you might agree with me. So one thing that is very difficult to show is whether a grammar is ambiguous or whether 2 grammars are equivalent. This ends up being an incredibly difficult question. It's actually relatively easy to answer yes, or sorry, it's relatively easy to answer no. Yes, it's ambiguous because we come up with the string and the 2 paths. Once we show that, then yes, it's ambiguous. But how do we show no, it's not ambiguous? That's tough. We have to say for every possible of the infinite strings that this grammar could generate, there's never more than 1 path that generates it. Much more difficult question. If 2 grammars are equivalent, it's very easy to show that they are not equivalent because we can show that we can generate one string in one and we can't generate that string in the other. But how do we show that they are equivalent? This would have to say for every possible string that could be generated by one, it could also be generated by the other and vice versa. That's a much harder problem. In fact, no algorithm exists that can answer those questions for every possible grammar. Obviously, for some grammars, you can intuit a solution or exhaustively iterate and show, but nothing in general works to be able to answer those questions given an arbitrary grammar. And we'll have the tools to show why that is by the end of this class. Not this class period, but this quarter. So just like we have ambiguous grammars, that means maybe it's not possible to create an unambiguous grammar for a language. There can be ambiguity baked directly into the language itself, such that there is no grammar representing that language that can be created that is unambiguous. Let's give you an example. Here is a language. First question I will ask you is this language context-free? If it is context-free, then we can write a grammar for it. So let's use this as an example and a chance to practice writing a context-free grammar. Go ahead and try to write a grammar that accepts this language. A to the n, b to the n, c to the m, union a to the n, b to the m, c to the m. It's not context-free? Interesting. Anyone else agree this is impossible to make a grammar for?
Possible to make a grammar or possible to make a
Regular.
grammar?
This could be context-free. So now we can, it does not have to be regular.
Well, if a context free means it must be regular.
No.
Oh.
It's if something is regular, then it is context-free. If something is context-free, it may not be regular.
Oh, okay.
So we can put those non-terminals in the middle of things now.
Huh?
It's definitely not regular. That is a very important distinction to make. But it's a little bit harder to see whether this is context-free or not. Whenever we see this union, we can think of this as something like left-hand side or right-hand side. So this is how I'd recommend getting started. So this language is context-free if we can find left-hand sides and right-hand sides for each of these sides of the union. Maybe that helps you.
I think it is context free. You can create it.
Think we have a solution?
I think so, but I'm not sure.
I'm curious. What do you have for the left-hand side?
So, okay, I have terminal A, capital A. B. Oh.
So we want. I want to extend from this because I want to extend from this idea of either handling the left-hand side or the right-hand side.
Or, right? So for the left side of the or.
Yeah. So just this portion of the left.
Yeah, so that's what I'm doing as well. So you have an A, right?
Yeah, we have an A.
Capital A. B. C. And then a capital C. And
Okay.
eventually my idea here is that for the A, we're gonna keep moving the A and B together, depending on how many N's there are.
Mm-hmm.
And then for the C, it doesn't matter because M is not related to N,
I
right?
think the issue here is we could have 0 of either of these. And you're forcing them to come together. As if we have anything, we have an A, at least one A and B and C.
Okay, yeah.
And they can also be equal to each other. There's nothing that says that N and M can have to be different. You're right, though, that this A being here would recurse making more A's and B's, and this C would recurse making more C's. But we need the ability to kind of do that separately, to kind of separate the concept of this and the concept of that. So I think we actually need 2 non-terminals here
Oh, I see.
that become this idea, and that way we can choose to do 0 of them. But it's a great idea. It has the exact structure of what we want. So I think we want something like, let's make this NL followed by ML, representing the N's from the left-hand side and the M's from that. So we're going to make the N's, we're going to make the M's. I'm going to say NL produces an A followed by an NL followed by a B or nothing. And ML produces a C and recurses on the right side of that. Be able to produce more C's. It actually doesn't matter where that is, where that recursion happens, but this just only allows us to see that we're making the C's at the end and we're recursing and making the same number of A's and B's in the middle. This allows us to make 0 or more of each of those pieces. And then we just have to do something very similar for the right-hand side. The right would go to, now the N comes first, and the M's are paired together. So we would have, again, NR followed by MR, where NR now makes A's in the front. So we're going to recurse in the front. And MR makes pairs of B's and C's. So this is going to be a B followed by MR followed by a C or lambda. This, I think, finishes it off. And adds a little bit of structure for kind of the left-hand side and the right-hand side, using non-terminals with the letters that are associated with the variables that are used in the language. I frequently like to do this just because it makes it a little clearer what the non-terminals stand for. Kind of like naming your variables something that's useful. It helps to kind of see this grammar at a bit higher level. But what do we think? Does this represent that grammar or represent that language? Anyone see any issues with this construction? Okay, now that if no one sees any issues with this, then we're going to assert that this is context-free, that this grammar represents this language. Since we can write a context-free grammar for this language is context-free. The next question that I would have for you is there ambiguity in this?
Yeah,
There is ambiguity. Where is it and how do we see it?
where the ML goes to CML, you were saying that we can recurse from either side, doesn't matter.
Yeah, but that would be options in the grammar itself.
Oh.
Looking at specifically this grammar. for a string, is there always going to be multiple parse trees that you could build for that string? What do we think?
I think if n is equal to n, then you could do either left or right at the start.
Yeah.
Give you the same string.
Yeah. Basically, at the beginning, when we read the very first character here, we need to make a very important decision. Left-hand side or right-hand side? And there's no way to know which side to go down at that point. There is ambiguity immediately, regardless of what the string is, because there's no way to force going down the left-hand side if that's the correct thing to do, or the right-hand side if that's the correct thing to do. You see an A, is it the left-hand side or the right-hand side? We don't know yet. There's no way to know. And if you can imagine trying to reconstruct this grammar, there's actually no way to construct this grammar in a way that you are sure of which path to take on a single pass from left to right. You have to analyze the rest of the string and then make that decision in order to remove that ambiguity. Let's see if I did this in a way that's going to overwrite what I did. So left side of the union, right side of the union. And then we have A to the n, B to the n, C to the n with two derivations. Yeah, combination will never be able to cover the case where n equals n. And we'll never be able to determine when n equals n, we can go either route. And it doesn't matter which route we go. There's no way to construct a grammar that makes it apparent which way to go, because we don't know if it's going to be equal yet. So that makes it very tough. All right, let's make this a little bit more solid. Apply it to things that we've seen before. So context-free grammars are incredibly important to programming languages because they involve the entire syntax. We use them for the entire syntax checking step. Does a program adhere to a language's syntax? Yes or no? That is what a compiler, that's part of what a compiler does. One of the first steps, just determine, can I create this program from the language's grammar? So, of course, we can define programming languages with grammars, and then we can do that precisely. Programming languages are often used, they use BNF, Backus NAR form, in order to do so. And this is just, we've actually seen this before in one of our homework assignments, the very first homework assignment. This is where you have non-terminals and angle brackets, and instead of arrows, you have colon, colon equals. But other than that, it's exactly the same idea. So we have terminals that are not in angle brackets and non-terminals that are in angle brackets, and that's just BNF. That's a typical way of representing a grammar once that grammar has an application. Obviously, whenever we can make productions clearer by making our non-terminals have a name associated with what they represent, the more understandable the grammar is. All right. Terminals and non-terminals in this production.
While
While is a terminal. What kind of grammar is this? While is a terminal, everything else is a non-terminal. We have now a way of representing, if we had further definitions for what an expression is and what a statement is, then we could determine when we have a while statement based on the keywords that are terminals. We just talked about this kind of grammar. What kind of grammar is it? It's a simple grammar. It has a single terminal followed by one or more non-terminals. So yes, this is a simple grammar production. The reason why we have the keyword before everything else is that it adheres to a simple grammar type of production. Why we type while before we do something, why we type for before we do something, why we type if before we do something, all of those are simple grammar productions. And that's consistent across just about every language that has those control structures. We always have the keyword followed by some syntax that distinguishes what are non-terminals that would evaluate to things like expressions and statements. So keywords are visual structure, but they are also terminals. They're exact key presses that represent an idea and tell us what we are about to do and what structure to look for after we see that keyword, which is why a simple grammar can't have multiple productions where you have a non-terminal arrow terminal and the same capacity. When we say while, we don't want to have two different possible structures for that while. We want to know when we see that while exactly what structure to expect from there. So it adheres to simple grammar's syntax. So makes the compilers work much easier. We don't have to interpret what comes after the keyword. The keyword tells us the structure of what is to follow. When you start to see that and recognize that when you're reading programming languages, learning a new programming language makes that a lot easier. You don't have to think about and memorize the order of things. It starts to make sense. Oh, this is just a simple grammar. Perfect. It makes sense why those come in the order that they come. Great. So expressions, not simple grammars, can't be simple grammars. But the higher level question that we're going to be answering through the rest of this class is what grammatical rules can we permit so that we can parse them efficiently? And we'll come back to this when we explore the linear time procedures, LL and LR grammars. And we'll do that at the very end. It's the last thing we discuss in this entire class. But that helps us to be able to understand what forms we can parse the most efficiently and what a lot of our programming languages are actually built around, so that when we do write compilers, those compilers will be efficient because of the design decisions that were made in the construction of the language. And having a deeper appreciation of that, again, makes learning new languages way faster. You can see the reasoning behind the decisions that were made. And that's really cool. That even applies to languages that are very different from languages that you've seen before. Has anyone written a program in a functional language? It's a big hole in our curriculum here at Eastern. We don't have a programming languages course that actually introduces you to functional language syntax. But functional languages don't have loops. They only have recursion. There are no variables, only bindings. You may pass functions to functions as parameters and return functions from functions. So it looks very different. I'll show this off in office hours to anyone who's curious. And maybe I'll do this at some point when we have a few minutes at the end of a class someday. But with 1 minute, I don't think I can quite do it justice. But it allows you to learn new kinds of languages as well, because even though it looks very different and it's hard to read, if you understand that higher level structure, you start to understand what's going on at that higher level. We are unfortunately out of time, so we'll have to come back to this tomorrow. I have my party starting in my office momentarily. Feel free to bring your own brain. I will see some of you there soon. Yes.
Oh, they're all the same. Hello, so.